Hello friends, it's a beautiful Sunday and I hope everyone is doing well. And my name is IBM and I would like to take you to another episode of Learning Physics. Specifically, we are dealing with waves and superposition, that is multiple choice questions. We are trying to solve these multiple choice questions. If this is your first time onto this YouTube channel, consider subscribing, consider downloading the documents so that you can use them for practice. Remember, like I said in part 1, this is going to be part 3. In part 1, I said multiple choice questions contribute about 10 out of 40 of the paper 1. Therefore, it's better you spend much time practicing them because they are the most important part of the syllabus. Multiple choice together with electricity will contribute the biggest percentage compared to all the other topics. Therefore, it's better you spend much time practicing them. So without wasting any much time, let's start part 3 and we shall go to the document. I think we stopped on page page 46. Maybe we stopped on this question where we said two progressive waves meet at a point P. The variation with the time t of the displacement of each wave at point P is shown here. So when you look at the graph, you notice that the period, because it's displacement against time, the period is actually 0.8. So we just need to look for two corresponding points. And I said, when you look at this wave here and look at this wave here, these are two corresponding points, and the time out of step, or the time between those two corresponding points, is actually 0.3. So we say the phase difference is going to be 360 divided by the time out of step over the period, which will be 360. The time out of step is 0.3 divided by the period, which is 0.8. And this would give us 0.3 divided by 0.8 times 360, which gave us 135. And we said the phase difference was 135. Okay, let's continue. A microphone connected to the Y plates of a CRO is placed in front of a loudspeaker. The trace on the screen of the CRO is shown here. The time-based setting is 0.5 milliseconds per centimeter, and the Y plate sensitivity is 0.2 millivolts per centimeter. What is the frequency of the sound from the loudspeaker, and what is the amplitude of the trace on the CRO? I will begin with the amplitude. So for the amplitude, I will try to look at the peak to peak. This is 1, 2, 3, 4, 5, 6. So the amplitude is going to be 6 divided by 2. That is 3. So the amplitude is going to be represented by 3 divisions, or 3 centimeters. The amplitude is going to be represented by 3 centimeters. So I'll multiply this by the Y plate sensitivity. So this is times 0.2 millivolts per centimeter. So per centimeter cancels. This gives me 0.6 millivolts. So it means I eliminate B and D. I remain with A and C. Okay, let's now find the frequency. To find the frequency is equal to 1 over the period, and this is 1 over the length, representing 1 cycle, times the time-based setting. So this will be 1 over the length representing 1 cycle. I think from here up to here we can consider that as 1 cycle. Or I can have 1, 2, 3, draw a horizontal line here. Although that will be hard for people to see that that is 1 cycle, this is easy from this point to this point. So this is 1, 2, 3, 4, 5, 6. So there are 6 centimeters representing 1 complete cycle. So this will be 6 centimeters length of 1 cycle times the time-based setting, which is 0.5. Now it is in milli, so I will say times 10 power negative 3. So now it will be seconds per centimeter. And of course, per centimeter cancels out. So the frequency is going to simply be 1 divided by 6 times 0.5 exponent negative 3. So this gives us 333, which is approximately 330. So this is approximately 330 hertz. So the answer is going to be A. The diagram shows an experiment to produce a stationary wave in an air column. A tuning fork placed above the column vibrates to produce a produces a sound wave. The length of the air column can be varied by altering the volume of the water in the tube. The tube is filled, and then water is allowed to run out of it. The first two stationary waves occur when the air column lengths are 0.14 and 0.42. Of course, it means the distance between the resonance points, distance between the two successive resonance points is going to always be half of wavelength. So it means the wavelength is going to be the distance between the two, which is going to be 0.42 minus 0.14. Then we multiply this by 2 from this expression here. So this is 0.42 minus 0.14, then times 2. So this is giving us 0.56. So the wavelength is 0.56. The answer is going to be D. A stationary person measures the speed and wavelength of the sound from a horn on a stationary vehicle. The person then repeats the measurements when the vehicle is approaching at a constant speed. Which row describes the measured wavelength and the measured speed of the sound wave from the moving vehicle when compared with the sound wave from the stationary vehicle? A stationary person measures the speed and wavelength of the sound from a horn on a stationary vehicle. So let's look at a stationary vehicle. Which row describes the measured wavelength and the measured speed of the sound wave from the moving vehicle when compared with the sound wave from the stationary vehicle? Okay, so A is saying it is longer. The person then repeats the measurements when the vehicle is approaching at a constant speed. So when it is approaching, the frequency is going to be higher. It means the wavelength is going to be lower. So the wavelength should be lower. That means we ignore A and C. The wavelength should be lower because it's approaching, the frequency is higher, the wavelength is lower. Then how about the speed of sound? Of course, the speed remains the same, so the answer is going to be D. The speed will not change, because if V is equal to lambda F, if F has increased and lambda has decreased, then it means V should remain constant. The table shows the wavelengths of 5 electromagnetic waves. Which row correctly identifies the principal radiation for each of these wavelengths? Remember, Remenera's or Richard's mother is visiting Uncle Xavier's garden. So this one has the shortest wavelength. Radio waves have the highest wavelength. So we are seeing that here the wavelength is increasing. The wavelength in A is increasing. Gamma rays have the smallest, followed by X-rays, gamma, X-rays, then infrared, then microwaves, and then radio waves. I think the answer is going to be A. Radio waves cannot have that small wavelength compared to the gamma rays. X-rays cannot have a smaller wavelength. I mean, X-rays cannot have a smaller wavelength than let's see, X. Okay, but X cannot have this wavelength. This is for gamma rays, so the answer is going to be A. Two progressive waves meet at a point. Which condition must be met for superposition of the waves to occur? For superposition to occur, of course, we know superposition, the waves must be of the same type, and they didn't talk about stationary waves, so the waves must be of the same type. That is enough. The waves must be of the same type. The waves must be coherent. Even if they're not coherent, as long as they are of the same type, superposition can occur. But if you want constructive, we want interference, or either constructive or destructive, then they should be from a coherent sources. A hill separates a television transmitter from a house. The transmitter cannot be seen from the house. However, the house has good TV reception. Of course, what is sending undergoes diffraction and can spread around the hill until it reaches the house. Therefore, by which wave effect at the hill could the TV signal reach the house? That is automatically diffraction. The diagram shows an arrangement for demonstrating two source interference using coherent light of a single wavelength lambda. An interference pattern is observed on a screen 3 meters away from the slits X and Y, which have a separation of 1 millimeter. So this is going to be A, slit separation. This is capital D. The central bright fringe is at Q, and the second bright fringe from the center is at P. What is the distance between Q and P? So this is the central bright fringe. This is the second bright fringe, which is at N equals to 2. So this is the first bright fringe. So we first need to get the distance between two successive bright fringes, which is small x. The wavelength has not been given, okay? So we shall simply say lambda is equal to ax divided by d, which means, or which implies that x is equal to lambda times d, which is 3, divided by a, which is 1 times 10 power negative 3. So x is going to be equal to 3 times lambda times 10 power 3. Yes, times 10 power 3 when this goes up. 3 divided by 1 exponent negative 3, that is 3000. Okay, or 3 lambda times 10 power negative 3. But then x is just the distance between two successive bright fringes. So it could be the central bright fringe and point P, and the first bright fringe. So if it is then the second one, it means the distance PQ should be twice this. So PQ should be 2 times 3 lambda times 10 power 3. So that is 6 times 10 power 3 times wavelength, which makes our answer to be A. Light of wavelength lambda is incident normally on a diffraction grating. The angle between the second order maximum and the normal to the grating is theta. The variation with sine theta of lambda is shown here. How many lines per millimeter are on the diffraction grating? So we know for diffraction grating, n times lambda is equal to d sine theta. So making lambda the subject, lambda is going to be d over n times sine theta. They have plotted a graph of lambda against sine theta, which means that the gradient is going to be d over n. And it is second order, so n is 2. So we want to find d first. So d is going to be equal to 2 times the gradient. Because n is 2, so it is 2 times the gradient, that is d. Remember, d is the slit separation, which is 1 over the number of lines. So this is going to be 2 times the gradient, which is just 750 minus 0 over, this is 0.6. So this is times 10 power negative 9. So d is going to be equal to that, 2 times 750 exponent negative 9 divided by 0.6. So this is 2.5 times 10 power negative 6. That is d. But the question does not want d. The question wants n. So n is equal to 1 over d. Remember, this is in meters because every quantity was in SI unit. So this is going to be 1 over, because they want the answer in per millimeter, it is easy to change this to millimeters first. So you can change this to millimeters. This is going to be 2.5 times 1000 will be times 10 power negative 3 in millimeters, so that your answer will be in per millimeter. So this will be over 2.5 times 10 power negative 3. So 1 divided by 2.5 exponent negative 3, and that gives us 400. That gives us 400. So n is equal to 400 per millimeter. So the answer is going to be A. A cathode ray oscilloscope displays a square wave as shown in the figure. The time-based setting is 0.2 milliseconds per division. What is the frequency of the square wave? What is the frequency of the square wave? So to find the frequency, we need it's 1 over the period, which will be 1 over the length representing 1 cycle times the time-based setting. So the frequency is going to be 1 over, if 1 cycle starts from here, so 1 cycle stops there. This is a second cycle. So this is 1, 2, 3, 4, 5, 6. So 1 cycle is represented by 6 divisions. So L is going to be 6 divisions. Then times the time-based setting, which is 0.2 times 10 power negative 3 per division. That is division power negative 1. So per division has cancelled. So you have 1 over 1 divided by open bracket 6 times 0.2 exponent negative 3. 1 divided by 6 times 0.2 exponent negative 3. So this is giving us 833.3 recurring, 830 approximately. So the answer is going to be B. A sound wave reduces in intensity but maintains a constant frequency as it travels through air. Which statement is correct? Number 1, remember it reduces intensity but maintains a constant frequency. Reduces intensity, maintains a constant frequency. Which statement is correct? The maximum displacement of the particles changes between one point and the next particle. Intensity is directly proportional to amplitude squared, and amplitude is the maximum displacement. So it means the answer is going to be A. Because the intensity reduces, the maximum displacement of the particles also reduces. Okay, the graph shows the variation with time of the displacement of an electromagnetic wave at a point. The wave is traveling in a vacuum. What is the amplitude and what is the wavelength of the wave? Of course, amplitude we see from the graph is 3. So B and D, those are going to be wrong. Then the wavelength, we can check the wavelength from here. No, there is no wavelength here. This is period. Period, we can find the period. Since we have, it is electromagnetic, so V is equal to lambda times F. The wavelength is going to be V. By the way, this is the same as lambda over T. So the wavelength is going to be lambda times T. Because F is 1 over T, so this is going to be V for electromagnetic is 3 times 10 power 8. Then T from the graph, this is 5 and this is 25. That's one complete cycle, so that is 20 times 10 power negative 6. So 3 exponent 8 times 20 exponent negative 6. That is 6,000. So the answer is going to be A. A long glass tube is almost completely immersed in a large tank of water. A tuning fork is track and held just above the open end of the tube as it is slowly raised. A louder sound is first heard when the height h of the end of the tube above the water is, that is the first time the loud sound is heard, that is the first position of resonance. The loud sound is next heard when the height is that. So remember we said the distance between two successive points of resonance is always half of the wavelength. So what is the frequency of the sound produced by the tuning fork? So wavelength is going to be 2 times the difference in those two values, that is 56.4 minus 18.8. So the wavelength is going to be 2 into 56.4 minus 18.8. So the wavelength is 75.2 in centimeters, or 75.2 times 10 power negative 2 in meters. Now we want to find the frequency. Frequency is going to be equal to, they gave us the speed, is going to be the speed over wavelength, which is going to be 330 divided by 75.2 times 10 power negative 2. So 330 divided by 75.2 exponent negative 2. So this is giving us 438.8, which is approximately 440. So the answer is going to be B. Source emitting sound of a single frequency Fs travels at constant speed directed towards the observer. The source then passes the observer and continues to move directly away. It first moves towards and then it moves away. The velocity of the source remains constant. V is constant. Which graph represents the variation with time of the frequency F naught of the sound heard by the observer? So of course, when it is moving away, the frequency is going to be high. When it is moving towards, the frequency is going to be higher. And when it moves away from the observer, the frequency goes below the natural frequency. So this one is showing frequency is initially below and then it is higher. That one is not true because when it is moving away, towards, the frequency is initially above, and then when it moves away, it becomes below. So this is going to be B. The rest are not correct, of course. This won't be a straight line. Since the speed is constant, this cannot be a straight line. It would be a straight line like this if the speed was increasing or decreasing. So this one also cannot be true. What are the names of electromagnetic waves that have wavelength in a vacuum of 100 picometers? 100 is 100 times 10 power negative 12. That is 1 times 10 power negative 10 meters. That is, I think, X-rays. So this is X-rays. So we ignore these two. Then 100 micros times 10 power negative 6, which is the same as 1 times 10 power negative 4. And I think that is infrared because Rumenera's mother is visiting Uncle Xavier's garden. When you look at the visible range, it is from 700, 7 times 10 power negative 7 to 4 times 10 power negative 7. This is violet, this is red. So it cannot be red because red is times 10 power negative 7. Therefore, the only option which we have there is infrared. So the answer is going to be C. The diagram shows a string stretched between fixed points X and Y. There is a stationary wave on the string. The solid curve shows the string at a position of maximum displacement. The dashed curve shows the other position of maximum displacement. The straight central dashed line shows the mean position of the string. Point S on the string is directly above point P. Point T on the string is directly above point Q. Which statement is correct? A short time later, point R on the string will be displaced. Now point R is at a point where there is a node, that means it is permanently at rest. Point S and T on the string move in opposite directions, that is very true. This is vibrating downwards and this is vibrating upwards on a stationary wave. So this is very true. The distance between P and Q is one wavelength. The distance between P and Q is one wavelength. No, it is less than one wavelength, because one wavelength will be either it is actually half a wavelength. P to Q, it is half wavelength. One wavelength would be X to R, or S to this point here. That's what we shall have as one wavelength. So P to Q is half wavelength. Then 2 points on the string that are equal distances from point R vibrate in phase. No, they actually, if, for example, Q and another point here, they are not vibrating in phase. They vibrate in 180 degrees out of phase. They are in antiphase. So the answer is only B. Which statement must be true for diffraction to occur when a wave passes through a gap? The wave is able to travel in a vacuum. The wave is progressive. The wave has a large amplitude. The wave has a long wavelength. So the answer is going to be B. For diffraction to occur, the wave must be progressive. In other words, it must be transferring energy from one point to another. That's how it is going to be able to spread through the gap, or it is going to be able to spread around an edge. So the answer is going to be B. The wave must be progressive for diffraction to occur. Light of a single wavelength is incident normally on two slits that are 0.2 millimeters apart. Interference fringes are observed on a screen that is 5.4 meters away from the slits. The distance between successive bright fringes is 12 millimeters. What is the wavelength of the light? So it is a diffraction. It is actually a double slit. Interference fringes are observed on a screen that is 5.4 meters away from the slits. So since it is a double slit, lambda is equal to AX divided by D. So we want the wavelength. Wavelength is going to be equal to A. A is the slit separation, which is 0.2 times 10 power negative 3. And then X, interference fringes are observed on a screen 5.4 meters. The distance between successive bright fringes is 12. So this is 12 times 10 power negative 3. Divide by D, which is 5.4. So we just press our calculator, 0.2 times 12 exponent negative 6. Divide by 5.4. So we get our answer as 4 recurring. That is going to be 4.44 recurring times 10 power 1, 2, 3, 4, 5, 6, 7 times 10 power negative 7 in meters. The answers have been given in nano, so we divide this by 10 power negative 9. To bring in nano, divide by 1 exponent negative 9. So this gives us 444.4 recurring, which is approximately 440. So this is approximately 440 nanometers. So the answer is going to be A. A diffraction grating and a screen are placed are used to determine the single frequency, the single wavelength lambda of the light from a source. What is the essential feature of this experiment? A diffraction grating and a screen are used to determine the single wavelength. What is an essential feature of this experiment? So we know that for a diffraction grating, if we want to determine a single wavelength, a curved screen must be used. Even if it is not curved, we can still find the wavelength. The diffraction angle theta must be measured for at least 2 interference maxima. We can still find the wavelength even if we measure 1. The light waves incident on the grating must be coherent, and this is going to be the most appropriate answer. Because if the light is not coherent, then it would be hard for us to measure, to determine for a single wavelength. If the light is not coherent, then it will form, if it is, for example, white light, then it will form a continuous spectrum, continuous patterns of the spectra on the screen. Therefore, since we want to determine the single wavelength lambda, then we need light of a single light from light waves incident on the grating that are coherent. That is, they maintain a single frequency. They maintain the same phase difference throughout. So the light waves incident on the grating must be coherent. The third order intensity maximum must be produced, not necessarily. So for the grating to be used to determine a single wavelength, then the light waves incident on the grating must be coherent. They must maintain a constant phase difference. A wave of amplitude A has intensity I. After passing through a certain medium, the wave has a new intensity of I/4. What is the new amplitude of the wave? So intensity is directly proportional to amplitude squared. For the first one, intensity is equal to K times amplitude squared. For the second one, the second intensity is going to be equal to K times the second amplitude squared. But the second intensity is I/4. This will be K times the second amplitude squared. So we combine. Where there is I will put there Ka squared. So I will say Ka squared over 4 is equal to Ka2 squared. So K cancels. And you notice that A2 is going to be the square root of A squared over 4, which is A/2. So it means the answer is going to be A/2, which is B. The wave travels along a coiled spring. The graph shows the variation with the time of the displacement of a point on the spring. What is the frequency of the wave? So this is displacement against time. So the period is going to be, let's say, from 0 to 0.2. We have, okay, 1, 2, 3 cycles. So 3 cycles have time of 0.4 seconds. That means one cycle will have time of 0.4 divided by 3. So we can find the frequency. Frequency is going to be equal to 1 over the period, which is going to be 1 divided by 0.4 over 3. So 1 divided by 0.4 divided by 3. 1, 2, 3. Okay. So that is 7.5. So our answer here is going to be D. So I counted 3 this time because I couldn't estimate a cycle here. It would be a wrong estimate. I took all 3 cycles. So this is time for 3 cycles. I divided by 3 to get time for 1 cycle, which is very accurate. A loudspeaker is set up at the open end of a closed tube containing powder. When the loudspeaker produces sound of frequency 1200 Hz, a stationary wave is produced in the tube. The powder gathers at the nodes of the stationary wave as shown in the figure here. The speed of the sound in the air is 336 meters per second. What is the value of x? So let's first find, they gave us the frequency and the speed. Let's first find the wavelength. So wavelength is going to be equal to the speed divided by the frequency, 336 divided by 1200. So the wavelength is going to be 336 divided by 1200. The wavelength is 0.28 meters. So let's find. Remember, whenever we see the powder, that is a position of a node. So this is a node. There's a node here. There's a node here. There's a node there. There's a node there. There's a node there. So if I was to sketch these, so x is corresponding to 1.5 wavelength. X is equal to 1.5 wavelength, which is 3/2 of wavelength. So that will be 3/2 times 0.28. That is 1.5 times 0.28, which gives us 0.42 meters, which is approximately 42 centimeters, or which is exactly 42 centimeters. So the value of x is 42 centimeters. A stationary source emits a sound wave frequency f. The source now moves away from a stationary observer. Which statement is correct? It moves away. So if it moves away, the frequency must automatically decrease. The frequency of the source S and the observed frequency are now both higher than f. A stationary source S emits a sound wave of frequency f. The frequency of the source will not be changing. It is the observed frequency which changes. The frequency of the source S and observed frequency are now both lower. The frequency of the source does not change. The frequency of the source S is now lower than f. The frequency of the source is not changing. The observed frequency is now lower. It is the observed frequency which becomes lower. The table lists possible wavelengths of 4 different electromagnetic waves. Which row is correct? Okay. So let's look at Rumenera's mother is visiting Uncle Xavier's garden. This is visible light, which is from 7 times 10 power -7 for red, and then up to 4 times 10 power -7 for violet. So 7 power -7 is approximately violet, so D is wrong. Ultraviolet is going to have, when I subtract 2 here, I get 10 power -9, that is ultraviolet. So 10 power -12 is most likely X-rays, that is wrong. Radio waves is most likely going to be a positive power, that is wrong. So the answer is going to be A. Infrared is approximately -5, -4, -6. A vertical tube is partially filled with water. A sound wave moves down the tube and is reflected by the surface of the water. The frequency of the sound wave is gradually increased from 0 until a much lower sound is heard. Water is then removed from the tube until a second louder sound is. This was a much louder sound is heard, and then a second louder sound is heard. Which diagram shows the new pattern of the stationary wave that is formed? Of course, there is always an antinode at the open end, so A is automatically wrong. And then, if this one is showing that there is an antinode at the end of the water, which is also wrong. This one is showing there is an antinode this side, which is automatically wrong. There should be a node at the surface of the water, so the answer is C. Water waves in a ripple tank are made to pass through a small gap as shown, which diagram shows the waves after they have passed through the gap. So of course this is wrong. This one is also going to be wrong. They are going to be broken wave like that. Then of course they are going, because the wavelength is approximately the same as the size of the gap, diffraction is going to be maximum, so the answer is going to be A. This one is showing you small diffraction, yet the wavelength is approximately the same as the size of the gap, so the answer is going to be A. A double slit interference experiment is set up using green light. A pattern of interference fringes is formed on a screen. Which single change will increase the separation of the fringes? It is a double slit, so lambda is equal to AX divided by D. Which single change will increase? We want the fringe separation to increase. Either wavelength increases, or D increases, or A decreases. One of those. Increase the width of each slit. We don't have, when we increase the width, X decreases. Move the screen nearer to the double slit. When you move the screen nearer, it means D is decreasing, which X decreases. Use slits that are far apart. Use slits that are far apart. Use slits that are far apart. That means you have increased the slit separation A, which also, if you increase the slit separation, it decreases X. Then use red light instead of green light. Red has a higher wavelength compared to green. And when we increase the wavelength, it means X increases. So since red has a higher wavelength, it means we have increased the wavelength. So the answer is going to be D. Use red instead of green because red has a longer wavelength than green. And when we increase the wavelength, X also increases. Light of a single wavelength from a distant point source falls normally onto a diffraction grating, positioned with its lines vertical, as shown here. The plane of the diffraction grating is at right angles to the incident light. A student looks at the grating from a position near to the grating. What could the student see? What could the student see? So because it is light of a single wavelength from a distant source is falling onto a diffraction grating positioned with vertical lines. So it means the student must also see a series of fine vertical lines on the screen. A series of fine vertical lines on the screen, which would be like the images of these slits. What could the student see? A central point source. That one is not true. A central vertical line with a series of spectra on either sides. That one is not true. This would be for white light, where we would see a central bright fringe with a series of continuous spectra on both sides. Then a series of fine vertical lines. The answer is going to be C. A single point source, not at all. The guitar string vibrates to create a sound. The speed of the wave in the guitar string is always 440 meters per second. The vibrating string creates a sound wave that moves in the air with a speed of 330 meters per second. So you see that the speed of the string is always higher than the speed of the vibrating string creates a sound. The speed of the string itself is greater than the speed of sound itself. And we know that V is equal to lambda times F. So the one with the higher speed will always have a higher frequency. Therefore, the graph for the string will always be above that of air. So it means we ignore D, because for D it is showing the graph of air is above that of the string, yet V is directly proportional to frequency. for the same wavelength. So we remain with C, then B, then A. For A, it is showing that as the wavelength increases, the frequency increases for both. First of all, this one is showing the graph of A is above that of the string. Now we remain with B and C. Because the speed of the guitar string is higher than the speed of the sound in air, the speed of the wave on this guitar string is always greater than the speed of the wave in air. This is showing us that for beat is showing us that as the wavelength increases, the frequency also increases, yet we see that frequency is inversely proportional to wavelength. So it means B is going to be wrong. So the answer is going to be C. The graph shows the variation with the time of displacement for two different waves, X and Y. So here we have said this graph was wrong because we know from this equation, wavelength is inversely proportional to frequency, so the graph would be C. The graph shows the variation with the time of displacement for two different waves, X and Y. Wave X has a frequency F and amplitude A. Wave X has frequency F and amplitude A. So this was a repetition. What is the frequency and what is the amplitude of wave Y? Okay. So we can try to look at the frequency. What is the frequency and what is the amplitude of a wave? So let's begin with the amplitude. Here the amplitude was A. The amplitude was A for wave X. This is 1, 2, 3, 4, 5. So 5 squares are representing amplitude A. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the amplitude for wave Y is going to be twice A. So we eliminate A and C. Now let's check the frequency. Of course, you see in one cycle of wave Y, there are two cycles of wave X. That means the frequency of wave Y is half that of wave X. So the answer is going to be B. A loudspeaker emits a sound wave into a tube initially full of water. A tap at the bottom of the tube is opened so that the water slowly leaves the tube. For some lengths of the air column in the tube, the sound heard is much louder. The first loud sound is heard when the air column in the tube has length x. The next loud sound is heard when the air column in the tube has length y. What is the wavelength of the sound from the loudspeaker? So we have said distance between two successive resonance points is always half wavelength. So this means y minus x is going to be equal to half wavelength, which means wavelength is going to be twice y minus x. So the wavelength here is going to be 2 times, the wavelength is going to be twice y minus x, which makes the answer to be C. A source of sound of frequency 1000 Hz directly approaches a stationary observer. The observer measures the frequency of the received sound to be 1500. The speed of sound in still air is 330. What is the speed of the source of sound? So observed frequency is going to be V over V, because the observed frequency is higher, so this is going to be minus the speed of the source, then times Fs. So this implies observed frequency is 1500, V is 330 over 330 minus Vs, then times 1000. So we just try to solve this. Solving this, I'll have 330 minus Vs is equal to 330 times 1000 divided by 1500. 330 times 1000 divided by 1500. So I'll just collect like terms. So 330 minus Vs is equal to 220. So Vs is going to be equal to 330 minus 220. 330 minus the answer, which is 110. So the answer here is 110. The graph shows how the intensity of EM radiation emitted from a distant star varies with wavelength. In which region of the electromagnetic spectrum is the radiation of greatest intensity? So greatest intensity is corresponding to around this area here. Just put there a ruler. So we have 200 nanometers. 200 times 10 power negative 9, which is 2 times 10 power negative 7. And that is after violet. This must be after violet because Romanera's mother is visiting Uncle Xavier's garden. For violet, violet is on the left-hand side, right-hand side, which is 4 times 10 power negative 7. This is violet. This is red, which is 7 times 10 power negative 7. So 2 times 10 power negative 7 is after violet, which is actually ultraviolet. So our answer here is going to be ultraviolet. Which statement concerning a stationary wave is correct? All particles between two adjacent nodes oscillate in phase. I think that is true. All particles between two adjacent nodes, if this is a node and there is a node here, all particles here vibrate in phase. All particles here vibrate in phase, but particles here vibrate 180 degrees out of phase with particles in this one here. Which waves would best demonstrate diffraction through a doorway? So you look for waves of the longer frequency because the doorway is relatively larger. So sound waves, we have sound waves, we have ultraviolet. These ones have a small wavelength of approximately 10 power negative 7 or negative 8. Visible light between 10 power negative 7 and negative 8, that will be very small. This is 10 power negative around 12 or 10. So it means it is sound waves. Okay, let's part one. Okay, I wanted part one to stop here. Two loudspeakers are placed near to each other and facing the same direction. A microphone connected to an oscilloscope is moved along a line some distance away from the loudspeakers as shown here. Which statement about the waves emitted by the loudspeakers is not necessary condition for the microphone to detect a fixed point along the line where there is no sound? In other words, to detect a point of destructive interference. Number one, the waves must be coherent. The waves must be in phase. Not necessarily in phase. In phase, that means constructive interference. So that is not necessary. The waves must be emitted from with a similar amplitude. That one is necessary for total cancellation. The waves must have the same frequency. That is necessary. Same wavelength. That is necessary. So even if they are not in phase, they're not emitted in phase, they may undergo destructive interference, because phase just means constructive interference. A parallel beam of white light passes through a diffraction grating. Orange light of wavelength 600 nanometers in the fourth order, so N is 4. Diffraction maximum coincides with the blue in the fifth order, so blue is 5. N is 5 for blue. What is the wavelength of the blue light? Okay, since it is a diffraction grating, we know that N lambda is equal to D sine theta. So let's start with orange. N for orange is 4. Wavelength is 600. I will not convert. 4 times 600 should be equal to D sine theta. But they said a parallel beam of white light passes through a diffraction grating. Orange light of that wavelength in the fourth order diffraction coincides with the blue light. That means sine theta is the same. So this is this sine theta. Then for blue, this is 5n times the wavelength, which we don't know. That should also be equal to d sine theta. That means the angle from the central bright fringe is the same for both. So we just equate these two. Wavelength is going to be equal to 4 times 600 divided by 5. 4 times 600 divided by 5, which is 480, making the answer to be B. The speed v of waves in deep water is given by this equation, where lambda is the wavelength of the waves and g is the acceleration of free fall. The student measures the wavelength and the frequency f of a number of these waves. Which graph should he plot to give a straight line to the origin? So we have that v squared is equal to g times lambda divided by 2 pi. We know that speed v is equal to lambda times f. When I square, it means this is squared, so it means lambda squared f squared should be equal to g times lambda over 2 pi. So lambda cancels out. We want a graph which gives a straight line. So f squared is equal to g divided by 2 pi times lambda. So the first graph, this is not a straight line. F squared is not even directly proportional to lambda. This one is also not a straight line, that we don't have f directly proportional to lambda squared. And this one will also not be a straight line. We even don't have f directly proportional to 1 over lambda. But we have this one, f squared is inversely proportional to lambda, which means f squared is directly proportional to 1 over lambda. So this one will give us a straight line. When sound travels through air, the air particles vibrate. A graph of displacement against time for a single air particle is shown here. Which graph shows how the kinetic energy of the air particle varies with time? When the displacement is maximum, the speed is 0. So here kinetic energy should be 0. 0, 0, 0, 0. So it means at t equals to 0, the kinetic energy should be 0. The graph starts from the origin, A is out, C is out. Number 2, at this point here, at half of t, kinetic energy should be 0 again. So half of t, kinetic energy should be 0. This one is showing it is maximum, so this is wrong. When displacement is maximum, kinetic speed is 0. When x is maximum, or when displacement is maximum, speed is equal to 0. That means kinetic energy is equal to 0. So that's why I said here it is 0, here it is 0, 0, 0, 0. At a half t, kinetic energy is 0. So this one is showing that half T kinetic energy is maximum. So the answer is going to be D. Because D we can see at T equals to 0, kinetic energy is 0. At T equals to half T, kinetic energy is again 0. At T, it is again 0. At 3/4 of T, it is again 0. So the answer is D. A vibrating tuning fork is held above a glass cylinder, above a glass cylinder filled to the top with water. The water level is steadily lowered. A loud sound is first heard when the water level is 83.5 centimeters above the bench. The next loud sound is heard when the water level is 17.1 centimeters above the bench. Remember, I said the distance between successive resonance points is half wavelength. So if we want wavelength, wavelength is going to be twice the distance, which is going to be 83.5 minus 17.1. So the wavelength is 2 into 83.5 minus 17.1, which is 132.8 in centimeters. That's the wavelength. So the question wants us to find the frequency. So let's find now the frequency. Frequency is going to be V over wavelength, which is 340 divided by wavelength, which is 132.8 times 10 power negative 2. 340 divided by 132.8 exponent negative 2. That is 256.0. So this is 256.0, 256.0 hertz. So the answer is going to be B, 256.0 hertz. Okay. An emergency vehicle sounds its siren as it accelerates along a straight road between 2 points X and Y, as shown in the figure. The frequency of sound emitted is 750. A person stands at X and another stands at Y. What describes the sounds heard by the people at X and at Y as the vehicle accelerates? The vehicle speeds up towards the other one, the speed increases because it accelerates. So frequency observed is going to be equal to V over V for X. For X, because it's moving away, this is going to be plus Vs, then times Fs. But now the vehicle accelerates, meaning the speed increases. The speed increases, Vs increases. When Vs increases, the denominator becomes bigger, which means this is going to become smaller. So the frequency by X decreases. So let's begin with X. Higher than 750, that's not true. Higher than 750, sound heard by the person at X is higher than 750 Hz, decreasing in frequency. It is not higher, it is actually going to be lower. So this is A. This is wrong. So lower than 750, we expect it to be lower. Lower than 750, we expect it to be lower. But decreasing in frequency or increasing in frequency. Because the speed is increasing, Vs is increasing because it is accelerating. It is going to be lower than 750 and also decreasing in frequency. Lower than 750 and also decreasing in frequency. Let's check for Y. F naught for Y is going to be V over, because it is approaching Y, this is going to be minus Vs n times Fs, but this is increasing. But because of subtraction, this is going to be smaller when Vs increases. That means F naught is going to be higher, first of all, because of the minus, And then as Vs increases, it is also going to be increasing. So higher than 750 and also increasing. So this is going to be C. Part of the electromagnetic spectrum is shown here. We have visible light, increasing frequency. What is the name of the shaded region, and what is the order of magnitude of wavelength of wave from this region? Remunera's mother is visiting Uncle Xavier's garden. If we have visible next on the left hand side, it is infrared. On the right hand side is ultraviolet. So the shaded region is ultraviolet. So we ignore A and B. Oh, they said frequency is increasing this side, so it is turning towards gamma. So gamma is this side. Frequency is increasing towards this side, meaning gamma is this side, radio waves are this side. Okay, so it means after visible, on the other side where we have a lower frequency, it must be ultraviolet. I mean, it must be on the other side where we have a high wavelength, that is towards radio waves, that must be infrared. So the answer is one of those two, A or B. Because they have showed us that frequency is increasing this side, so it is this side we have gamma. So it means we have gamma, X-rays, ultraviolet, visible, infrared, microwaves, and then radio waves. So that is infrared, so we ignore C and D. Then, if it is infrared, it is just after red. So the frequency, this one is smaller, yet is supposed to be larger since it has a longer wavelength. So the answer is going to be A. The three waves shown in each diagram have the same amplitude and frequency but different phase. They are added together to give a resultant wave. In which case is the resultant wave zero at this instant? Resultant wave zero. So let's begin with A. We have three waves. This is like, that is its amplitude. For these two waves are meeting here, their amplitude adds up. If one has let's say, and actually this is half, almost half of the other one, but it adds up, so it is half plus a half, which is equal to the other one. So it means these ones will give a resultant here, which is like this. This is the resultant of these two which are meeting at these points. And therefore, it means if they meet at this point and give this resultant, a crest is meeting with a trough. That is constructive interference, which means they added up to give constructive interference, but then their resultant combines with the other crest. So the trough here is going to which is formed by these two is going to combine with the trough with the crest up. So there is total cancellation, giving us a horizontal line. That means the resultant will be zero. So the answer will be A. This one is wrong. These ones, you see that they will never form a resultant zero. Here, when these two add up, they will give an amplitude which is bigger than this. They will add up and give a bigger amplitude here at this point, which is going to be almost twice as this. So there is no destructive interference here. Similarly here, these ones, when they are adding up, there is no possibility of them forming a resultant of zero because there is no crest. There is no possibility of a crest meeting even with a trough. So our answer is going to be A. I said it is A because here where these two meet, the amplitudes add up. And we see that this part here is almost half of the other one up. So when they add up, it becomes half plus a half, which is almost equal to the other one on top. But because this will be a trough downwards, it will combine with the crest upwards so that the resultant will be zero. A transmitting a transmitting must send a transmitting must send out microwaves of wavelength 1.5 centimeters and radio waves of wavelength 1.5 kilometers. A receiving area behind a mountain can detect the radio waves, but not the microwaves. What is the reason for this? What is the reason for this? Number one, the radio waves are coherent, but the microwaves are not. That is not the reason. The reason must rely on diffraction because microwaves cannot easily be diffracted as compared to uh, radio waves. Radio waves have a longer wavelength than microwaves. They say it sends microwaves of this and radio waves of 1.5 kilometers. So the wavelength of radio is greater. So it means they can easily undergo diffraction because of the larger wavelength than the microwaves. The radio waves are diffracted around the mountain, but the microwaves are not. So that is going to be our answer. The microwaves are not easily diffracted because of their small wavelength. An experiment is carried out to demonstrate double slit interference using light of wavelength 500 nanometers. The distance between bright fringes in the interference pattern is 5 millimeters. What are the possible values for the distance between the slits and the screen and the separation? Okay, and the slit separation. So we know that for double slit, lambda is equal to AX over D. Lambda is AX over D. So they gave us the wavelength. So we shall say 500 times 10 power negative 9 is equal to the distance between bright fringes. So X is 5 millimeters. So that will be 5 millimeters times 10 power negative 3 times A divided by D. So we know that A times 5 times 10 power negative 3 should be equal to 500 times 10 power negative 9 D. Okay, so it means A should be equal to 500 times 10 power negative 9 d over 5 times 10 power negative 3 times d. Let's first simplify that. 500 exponent negative 9 divided by 5 exponent negative 3. So that is 1 times 10 power. So A should be equal to 1 times 10 power negative 4 times d. In meters, of course. Okay, so let's check. Let's check. Slit screen distance, this is D and this is A, slit separation. So let's check. Let's compare. In other words, when we divide A by D, we should get 1 times 10 power negative 4. So let's just check that. A divided by D, what do we get? A is 0.5 exponent negative 3 divided by D, which is 50 exponent negative 2. So this is giving us 1 times 10 power negative 3. So this is wrong. Let's check the second one. A is 5 exponent negative 3 divided by D, which is 50 exponent negative 2. This is wrong. Let's check the third one. 0.5 exponent negative 3 divided by 5 meters. So this is giving us 1 times 10 power negative 4. So the answer is going to be C. Because we have seen that A divided by D should be giving us 1 times 10 power negative 4. So the answer is going to be C. Light of a single frequency is incident on a diffraction grating. 7 bright spots are observed on a screen. 7 bright spots are observed on the screen. which change will result in an increase in the number of bright spots. For diffraction grating n, lambda is equal to d sine theta. D is remaining constant, okay? So the number of bright spots is n. The maximum order is equal to d sine theta divided by lambda. We want to increase the number of bright spots. We must either decrease wavelength or increase d and increase the distance between the grating and the screen. Increase the distance between the grating and the screen. This one does not increase the number. Increase the frequency. Of course, increasing the frequency, if frequency is increased, it means the wavelength is decreased. When wavelength is decreased, if we are seeing wavelength is inversely proportional to n, so n will therefore increase. So the answer is going to be B. Two waves x and y have the same frequency. The amplitude of x is 1.5 a0 and the amplitude of y is 2.5 a0. The waves meet at a point and superpose to form a resultant velocity. For the resultant wave, what is the ratio? Maximum possible intensity over maximum possible intensity. Maximum possible intensity over minimum possible intensity. So two waves x and y have the same frequency. The amplitude of x is 1.5 a0 and the amplitude of y is 2.5 a0. The waves meet at a point and superpose. So maximum possible intensity, remember intensity is directly proportional to amplitude squared. So if they superpose uh, constructively, then it means the resultant amplitude, so let this be, let's say intensity of x is going to be equal to k times amplitude of x squared, which is k times 1.5 a0 and this is squared. Then when they superpose, the resultant intensity, the maximum possible intensity, is going to be equal to, the maximum possible intensity could be, when the amplitudes add up, would be the constant k times amplitude of x, which is 1.5 a0 plus 2.5 a0, and this is going to be squared. This is for maximum. Then for minimum, intensity minimum is going to be equal to k into, now this will be a difference, that will be 2.5 minus 2.5 a0 minus 1.5 a0, and this will also be squared. So we can find the ratio. So the ratio k cancels out, and you will have maximum, which is 1.5 plus 2.5, which is 4.0, that is 4 a0, and this is squared, divided by this is 1.5 minus 2.5 minus 1.5, that is 1.0 a0, and this is also squared. So I'll just have a0 has cancelled, so I remain with 4. I remain with the 4 divided by 1 and squared, so that is going to be 4 squared, which is automatically 16. So the answer is going to be D. This is going to be 16. The displacement time graph for any air particle in the path of a sound wave is shown here. Which property of the sound wave must be increasing? So we see that the period for the first one took this time, took a smaller time, so the period is decreasing. Period is decreasing, it means the frequency must be increasing. Which property of the sound wave is increasing, that is the frequency, we see that the waves are getting closer. They are taking a smaller and smaller time. That means period is decreasing, which means the frequency must be increasing because frequency is equal to 1 over period. So if the period is decreasing, the frequency must be increasing. A sound wave is displayed on the screen of a cathode ray oscilloscope as shown here. The time base of the CRO is 2.5 milliseconds per centimeter. What is the frequency? So we know that frequency is going to be 1 over period, which is going to be 1 over the length of one cycle times the time base setting x. So this is 1 over, for one cycle, is represented by 1, 2, 3, 4 boxes. That is 4 centimeters. So that is 4 centimeters times time base setting, which is 2.5 times 10 power negative 3 to change it to seconds per centimeter. So per centimeter cancels with that. So you remain with 1 divided by 4 times 2.5 exponent negative 3. So the answer here is going to be 100. The horn of a train emits sound of frequency F1. Where the horn is sounding, the train moves directed towards a stationary person. The speed of the train is 0.2 v, where v is the speed of sound. The frequency of the sound heard by the person is F2. What is the ratio F1 over F2? So let's find F2 first. The observed frequency is going to be V divided by V plus, because it is moving towards, so this is going to be minus. So this will be minus speed of the source, then times the horn of the train emits sound of frequency F1. So this will be times F1. So it means F2 is going to be V is remaining V over V, where there is speed of the train is 0.2 V, then times F1. So I want F1 over F2. F1 over F2 is going to be, this one is going to be V minus 0.2 V divided by V, which is 1 minus 0.2. So F1 over F2, V has cancelled. It is a common factor, V into 1 minus 0.2 over V. So this is 1 minus 0.2, that is 0.8. So F1 over F2 is going to be 0.8 divided by 1. So the answer is A. Two satellites in orbit around the Earth are at constant distance of 100 kilometers apart from each other. Satellite X transmits a microwave pulse towards satellite Y. The pulse takes time t to reach Y. Satellite Y then transmits a pulse of visible light towards satellite X. What is the time taken for the pulse of light to reach X? Now light, they are traveling at the same speed c, which is 3 times 10 power 8 meters per second, and they are going to travel the same distance. So speed is the same, distance is going to be the same. So time being distance over speed, because speed is constant, so the time is going to be the same. So the answer is going to be T. The pulse takes time t to reach Y, and then light is going to travel towards X. So it will also take the same time. Visible light will also take the same time. A stationary wave is formed on a stretched string. The diagram illustrates the string at an instant of time when the displacement of the string is at its maximum. The frequency of the wave is 250 Hz. Point P on the string has a vertical displacement of negative 1.0 millimeters. What will be the vertical displacement of the point P after a time of 5 milliseconds? So let's first find the period. Period is going to be 1 over frequency, which is 1 divided by 250. 1 over 250, which is 4 times 10 power negative 3 seconds. Let's change it to milliseconds. Divide by milli, that is 1 exponent negative 3. That is 4 milliseconds. So 4 milliseconds. So what will be the vertical displacement of the point P after time of 5 milliseconds? We are saying the period is 4 milliseconds. So that means 5 milliseconds is equal to 4 milliseconds. That is 4 complete cycles plus 1 millisecond. And 1 millisecond is going to be a quarter. So we have 4 cycles plus a quarter a cycle. 4 cycles plus a quarter cycle. Or in other words, we could say 5 divided by 4. So the number of cycles is 5 divided by 4. 5 over 4 cycles in total. So let's just find one cycle, the distance traveled by one cycle. So if it moves, it is starting from here. Point P on the string has a vertical displacement of negative 1.0 millimeters. So going upwards, let's say P starts from here, it covers 1.0 meters, it goes up 1.0, it comes back 1.0, it comes back to point P again to its initial position 1.0. So that is, so one cycle is going to be equal to a distance of 1.0 times 1, 2, 3, 4. 1, 2, 3, 4. Here it is going upwards, downwards, back to its initial position. So 1.4 millimeters. So one cycle is going to be 1.4. 1 times 4 millimeters, which is going to be 4 millimeters. So in one cycle it covers 4 millimeters. Then we have 5 over 4 cycles. So total distance is going to be equal to, what will be the vertical displacement of the point P after a time of 5.0 milliseconds. Okay, total distance, let me first find total distance, will be 4 times 5 over 4, which will be 5 millimeters. So total distance will be 5 millimeters. Total distance will be 5 millimeters. So let's say it moves upwards, coming back, this is 4 millimeters, then 5 millimeters has to go back to equilibrium position. That means the displacement is going to be 0. So this total distance is supposed to be 5 millimeters, but displacement is a vector quantity. So it goes back to equilibrium, so displacement will be 0. Okay. What is meant by diffraction? Of course, diffraction is spreading of a wave into regions of geometrical shadow. So spreading of a wave around the edge of an obstacle, that is diffraction. In a darker room, a small source of red light illuminates two slits that are 0.7 millimeters apart. A few meters beyond the slits, the light falls on a screen, producing a series of equally spaced bright lines. Which change would cause the distance between the bright lines on the screen to be reduced? So since we have two slits, that is double slit, so lambda is equal to ax divided by d. Which change would cause the distance between the bright lines, that is x, to be reduced? Either wavelength decreases. Do we have wavelength here? Or frequency increases. We don't have wavelength here. Then we want this to decrease, so d must decrease because they are directly proportional. Distance between the source decreases, reduce the distance between the light source and the slits. And I think this reduce the distance between the light source and the slits. In a dark room, a small source of red light illuminates two slits. That one has no effect. This is not the distance D. So we have the source here, we have the slits here. D is the distance between the slits and the screen. They are saying reducing this distance here. That one does not have an impact on X, just affects the intensity. Reduce the distance between the slits to 0.55 millimeters. Reduce the distance between the slits, that is reducing A. When we reduce A, X instead increases because A is inversely proportional to X. So this one and this one are not working. Reduce the intensity of the light source. That just affects the brightness. So it means the answer is going to be a change the source for one emitting blue light. Change the source for one emitting blue light. What have we done? We had red light initially. Now we have removed red and put blue. We have actually reduced the wavelength because Richard of York gave birth in vain. Blue light has a smaller wavelength than red light. This is decreasing wavelength. Blue light has a smaller wavelength than red. When we decrease the wavelength, it means when wavelength decreases, X also decreases because they are directly proportional. So the answer is A. Light of wavelength 5 times 10 power 5.3 times 10 power negative 7 is incident normal on a diffraction grating. The first order maximum is observed at an angle of 15.4 degrees to the direction of the incident light. What is the angle? What is the angle between the first order and the second order? Okay. Light of wavelength, this is incident normal on a diffraction grating. The first order maximum is observed at an angle of 15.4 degrees to the direction of the incident light. So it means n lambda is this sine theta. So what is n is 1, wavelength is 5.3 times 10 power negative 7. What is missing here is d sine of 15.4. Let's find d. So d is going to be 5.3 exponent negative 7 divided by sine of 15.4. So d is approximately 1.996. D is 1.996 times 10 power negative 5 in meters. So what is the angle between the first order and the second order? Let's find the angle of the second order. So n is 2, so it will be 2 times wavelength is 5.3 times 10 power negative 7 is equal to d, which is 1.996 times 10 power negative 5 sine of the angle theta 2. So you have 2 times 5.3 exponent negative 7 divided by 1.996 exponent negative 6. Then get the sine inverse. So theta 2 is 32.1 degrees. Theta 2 is 32.1. Now we want the angle between. So we get 32.1 minus 15.4 minus 15.4, which is 16.67, approximately 17. Let's see which answers we have here. We have 7.7, 15 point that, so we have 16.7. So the answer is going to be C. A transverse wave on a rope has wavelength lambda and period t. The graph shows the variation of the displacement of the particles of the rope with the distance in the direction of travel of the wave at time t equals to 0. A particle x is labeled. Which graph shows the variation of the displacement of particle x with the time t? Displacement of particle x with the time t. So at t equals to, so they have sketched displacement against distance. So let's say this particle here, this is a full wavelength. Because it is displacement against distance, the particle here at t equals to 0, x is passing equilibrium, so it must have this 0 displacement. X is at equilibrium, it must have 0 displacement, but then it is vibrating downwards. That means after a quarter a cycle, it should be at maximum displacement downwards. So this one is showing after a quarter cycle, it is at maximum displacement upwards, which is wrong. This one is even showing starts at t equals to 0, the displacement is 0, which is wrong. This one is also wrong because at t equals to 0, it is showing displacement is not 0, yet we see at t equals to 0, x is at equilibrium, so displacement should be initially 0. So it means our answer is going to be C. Here the particle was vibrating downwards, it was just passing equilibrium, but vibrating downwards. So it means at t equals to, when it reaches at half wavelength, it must have reached a maximum displacement downwards. That is why the graph is going to be that of C. Which statement about all types of transverse waves is correct? Transverse waves. They undergo polarization. And we have polarization here. They all have the same speed. Not really. Not all transverse waves are electromagnetic. It is only electromagnetic waves with the same speed. They all have vibrations that are parallel. Vibrations are actually supposed to be perpendicular. They can all form stationary waves. They can all travel through a vacuum. They cannot all travel through a vacuum, but at least they can all form stationary waves. Not all transverse waves travel through a vacuum. It is only electromagnetic waves that travel through a vacuum. Source S emits microwaves with a constant amplitude. The microwaves hit screen P and are reflected. The stationary wave is formed between S and P. The wavelength of the microwaves is much smaller than the distance between S and P. A detector Q is moved at a slow constant speed from S to P. What happens to the amplitude of the signal detected by Q? They said the wavelength of the microwaves is much smaller than the distance between S and P. Remember, a distance between two successive points where there is nodes or antinodes is half wavelength. So it means the wavelength is going to be twice the distance between two successive points of nodes or antinodes. But they say the wavelength of the microwaves is much smaller than the distance between S and P. A detector Q is moved at a slow constant speed from S to P. It is moved from S to P. What happens to the amplitude of the signal detected by Q? Of course, we know that at P we expect there to be a node. We expect at P to be a node. If P is the reflector, we expect a node here. So what happens to the amplitude? it decreases steadily. Of course, it is going to actually increase and decrease. So the answer is going to be B. It increases and decreases gradually. Because towards P, it must be 0. It must go to 0 because this is like a point of reflection where this is going to be a node. So it increases and decreases regularly. The siren of a moving police car emits a sound wave with a frequency of 440 Hz. A stationary observer hears sound of frequency 494 Hz. The speed of sound in air is 340 meters per second. What could be the speed and direction of movement of the car? We notice that what is observed is a higher frequency, so it must be towards. So we ignore away, we ignore away. So let's now check the speed. So observed frequency is equal to B over V because it is towards, so it is minus Vs divided by times the frequency of the source. So 490 is equal to 340 divided by 340 minus V of the source times 440. So I will say 340 minus V of the source is equal to 340 times 440 divided by 490. So we solve that. 340 times 440 divided by 490. Then this gives us that value. So we shall say 340 minus that. 340 minus the answer. So it means Vs is going to be equal to, is it 34? Let me check it again. 340 times 440 divided by, this is 94, not 90. So it means the answer is A. So let's check. Divide by 494. So I have 340 minus the answer, which is 37. So the answer is 37. An EM wave has a wavelength of 138 picometers in a vacuum. To which region of the electromagnetic spectrum does this wave belong? So 138 times 10 power negative 12 meters. This is the same as 138 exponent negative 12 is 1.38 times 10 power negative 10 meters. This is X-rays. This is probably X-rays. Because visible light will be 10 power negative 7. Radio waves could be 10 power negative power 2. Microwave 10 power negative 2, negative 3. Two wave pulses are traveling towards each other on a long rope. The pulses have the same amplitude and wavelength and are traveling at a speed of 0.5 meters per second. The diagram shows the rope at time t equals to 0. Which diagram shows the rope at time t equals 3.0 seconds? Let's first find the period. They have given us the speed as 0.5. They have given us the speed as 0.5. We can see the wavelength for this one. The wavelength is going to be 1.5. So that means the period is going to be, or V is equal to lambda times F. We don't have F. We have the speed. So V is equal to lambda over T. So meaning the period is going to be wavelength, which is going to be the wavelength is 1.5 meters divided by the V, which is 0.5. So it means the period is equal to 3 meters per second. So when they say which diagram shows the rope at t equals 3, that is after one complete cycle. So after one complete cycle, we expect that this will have one wavelength must have moved forward for each of these waves. And this would mean after one cycle, so this must have shifted to this point here. So this shifts to this point here, and this part here will also have shifted. So we shall have a wave here, which is going to be somehow like this. For this one, let me maintain the same amplitude. After one cycle, after 1.5, so this we shall be here. So we shall have something like this. Why is it hard for me to sketch this? For this one, then for the other one, because it was moving to the right, I'll change the color for it. For this one, we shall also have it here, because this is it will have shifted. So we shall have it here also. So what will be the net resultant then? The net resultant at that point will be addition of these amplitudes. So this means, because when you look at this is going to add to this is going to add to that, this is going to add to this, and this will add to this. So the resultant would be actually the sum of those two. I'll represent the resultant with green. So the resultant would be, because the amplitudes are adding up, so we shall have such a resultant. So this means our answer is going to be C. Light of wavelength 720 nanometers from a laser X is incident normal on diffraction grating, and a diffraction pattern is observed. Light from a laser Y is then also incident normally on the same grating. The third order maxima due to laser Y is seen at the same place as the second order. That means theta is the same for the third of Y and the second of X. What is the wavelength of the light from laser Y? So for diffraction grating, n lambda is equal to d sine theta. For diffraction grating for Y, which is a third order, its wavelength is not known. I'll call it lambda for Y is equal to d, it is the same grating, and then sine theta, it is in the same place because the orders are appearing in the same place. Then for X, it is a second order, so this is 2 times the wavelength of X, which is 720, is going to be d sine theta. So I just equate these two equations. So it means wavelength of Y is going to be equal to 2 times 720 divided by 3. 2 times 720 divided by 3, which is 480. So the answer here is going to be 480. Monochromatic light of frequency f is incident on a diffraction grating of line spacing d. The speed of light is c, which expression can be used to determine the highest order of intensity maxima produced. So for the highest order, sine theta is going to be 1. So n lambda is equal to d sine theta. That means n is going to be d over lambda. But remember, from v equals lambda f, v is given as c. C is going to be equal to c over f is equal to lambda. So we substitute for lambda here. It means n is going to be d divided by c over f. which means this becomes d times f over c. So the answer is going to be d times f over c, which is going to be B. A transverse wave is traveling along a rope. The frequency of the wave is 2 Hz. The graph shows the variation with distance of the displacement of the wave at time t equals to 0. Which diagram shows the position of the wave at time t equals 0.5? Let's first find the period. Time for one cycle, period is going to be 1 over 2, which is actually 0.5. Period is 1 over 2, which is 0.5 seconds. So which diagram shows the position of the wave after half a cycle? After half a cycle, this was at t equals to 0. Then after half a cycle, so after half a cycle, a crest, a transverse wave is traveling along a rope. The frequency of the wave is 2 Hz. The graph shows the variation with the distance of the displacement of the wave at t equals to 0. At t equals to 0, this is what we have. Then at t equals to 1, the period is 0.5 seconds. Which diagram shows the position of the wave at t equals 0. That is after one cycle. Oh, that is very simple. It will be exactly the same. So this is going to be D. Exactly the same as this. It will have almost exactly the same shape as that one. So that is going to be D. So this will be after half a cycle. This will be after half a cycle. This is half a cycle, which is half of a period, but that will be 0.25 seconds. But then after a full cycle, we go back to the same position. The two graphs represent the same wave. Graph 1 shows the variation with the time of the displacement at a particular distance. Graph 2 shows the variation with the distance of the displacement at one instant. They are looking at the same wave. What is the speed of the wave? So speed is equal to lambda times f. So wavelength, we shall look at this one. Which wavelength is going to be, this is 15, and this is 50, 60, 75. So that is 75 minus 15, which is 0, that is 60. So the wavelength is 60 times 10, okay, 60 centimeters. Then the frequency is, this is divided by V is equal to lambda over T. So this one I will divide by T instead of multiplying. The period is 0.5 seconds. Time for one cycle, 0.5 seconds. And this means I have 60 divided by 0.5, which is 120. So it means the answer is going to be 120 centimeters per second. A microphone is connected to a cathode ray oscilloscope. When a tuning fork is struck and then held next to the microphone, the following waveform is shown on the display of the CRO. The time-based setting on the CRO is 2 milliseconds per division. What is the best estimate of the frequency of the sound produced by the tuning fork? Okay, so let's get one cycle is represented by 2 divisions. So frequency is equal to 1 over period, which is 1 over the length of one cycle times the time-based setting. 1 over the length is 2 divisions. So we have 2 divisions. Time-based setting is 2 times 10 power negative 3 per division. That is seconds per division. So per division cancels out. So we have 1 divided by 2 times 2 exponent negative 3, which is giving us 240 250. So the answer is going to be C. A loudspeaker emitting a constant frequency of 200 Hz is swung in a horizontal circle with a speed 15 meters per second. A stationary observer is level with the loudspeaker and situated a long distance from the loudspeaker. The observer hears a sound of varying frequency. The maximum frequency heard is 2097, which is higher. What is the speed of the sound in the air? So the observed frequency is 2097, which is equal to the speed v divided by, and a stationary observer is level with the loudspeaker. So this loudspeaker is moving towards, so we shall subtract. So this is going to be v minus 15, then times 2000. So we have to solve this. Okay, we shall solve this. So we shall have 2000 times v equaling to 2097v minus 20 times 15. So 2097 times 15, 31,455. Okay, so we collect like terms. So we have 2000 minus 2097. Then we get 3131. Okay, we have negative 97v equals to 31 negative 455. 31,455 divided by 97, which gives us 324. So the answer is going to be C. So V of the source, sorry, V, not V of the source. Speed of sound is going to be 324. So our answer here is going to be C. Two electromagnetic waves have wavelength 5 exponent negative 7 and negative 2 meters. Which row identifies them? Negative 7 is visible spectrum, so we ignore ultraviolet, and then negative 2. We have microwave and infrared. Infrared is approximately negative 4, negative 5, so the answer is going to be B. A transmitter of electromagnetic waves is placed 45 centimeters from a reflective surface. The emitted waves have a frequency 1 gigahertz. A stationary wave is produced with a node at the transmitter and a node at the surface. There's a node at the transmitter and a node at the surface. How many antinodes are in the space between the transmitter and the surface? Okay, so the emitted frequency is going to be equal to the speed divided by wavelength, and they have told us that the distance a transmitter of electromagnetic waves is placed 45 centimeters from a reflective surface. And they are telling us there is a node at the transmitter and a node at the reflector. The emitted waves have a frequency of 1 gigahertz. The emitted waves have a frequency of 1 gigahertz. A stationary wave is produced with a node at the transmitter and a node at the surface. How many antinodes are in the space between the transmitter and the source? Let's first find the wavelength. So wavelength is going to be equal to frequency, which is 1 times 10 power 6. No. So the wavelength is going to be V, which is because it's electromagnetic, V is 3 times 10 power 8, divided by the wavelength, divided by the frequency, which is 1 times 10 power 6 giga, that is power 9. So this is going to be 3 exponent 8 divided by 1 exponent 9. So that is 0.3. So the wavelength is 0.3 in meters. So that is the wavelength. And so since we have the wavelength, we want to find how many distance between two successive antinodes is always half wavelength. Distance between two successive antinodes is half wavelength. In other words, also the distance between two successive nodes is half wavelength. So the question is, how many antinodes are there? For every two antinodes, the distance between two successive antinodes is half wavelength, which is going to be equal to a half times 0.3, which is going to be equal to 0.15 meters. So the distance between two antinodes, successive antinodes, is 0.15 meters, which is also the distance between two successive nodes. So how many antinodes are in the space between the transmitter? So I'll just say 45 centimeters, which is 0.45 divided by 0.15, then minus 1. And I think here the answer is going to be, let me check it again. No, there's not need of subtracting 1. How many antinodes? Okay, let me find the distance between successive nodes. The distance between successive antinodes is half wavelength, and we have said 45 divided by 100, which is 0.5, then divide by 0.15, which is 3. So I think the answer is going to be 3. Number of antinodes is equal to 3. We can check. Manually, we can check. If we have, there is a node here and a node here, and the distance between every antinode is 0.15 or 15 centimeters. So let's say 15 centimeters. This is 15. This is another 15. And this is another 15. 1, 2, 3. So there are 3 antinodes. 3 antinodes, because the distance between two successive antinodes should be 15 centimeters, which is going to also be the distance between two successive nodes. So this is going to be 3. Which statement about a light wave and a sound wave is correct? Both can travel through space, free space. A sound wave cannot travel through free space. It requires a material medium. Both have frequency inversely proportional to wavelength. That is true. Both have intensity proportional to the amplitude. Intensity is proportional to amplitude squared. Both have oscillations perpendicular. No, for sound it is parallel. So the answer is B. An electromagnetic wave is incident normal on a diffraction grating. A second order maximum is produced at an angle of 30 degrees to a normal to the grating. The grating has 5,000 lines per centimeter. That means number of lines per meter is going to be 5,000 times 100. What is the wavelength? So since it is a diffraction grating, n lambda is equal to d sine theta. And d, remember, is equal to 1 over the number of lines per meter. So wavelength is going to be d, which is 1 over 5,000, then and 2 zeros, which is going to be 500,000, sine of theta, which is sine 30, then divide by n, it was the second order, so n is 2. So we shall simply say as sine of 30 divided by 2 times 500,000, which is 5 times 10 power negative 7. So the answer is going to be B. Which statement about light waves and sound waves is not correct? Light waves and sound waves can both demonstrate Doppler effects. That one is true. In light it is Doppler. Although for sound it is Doppler, for light it is redshift. Light waves are transverse and sound waves are longitudinal. That is also true. Light waves can be diffracted, but sound waves cannot. Which statement about light waves and sound waves is not correct? Both of them can undergo diffraction, so this statement is not correct. The graph represents a sound wave. Which statement is correct? The wave is longitudinal and has a period of 25 milliseconds. Let's first check the period. The period is not 25, it is actually 20. The period is actually 20. The wave is longitudinal. The wave is longitudinal and has a frequency of 50 Hertz. The wave is longitudinal and has a frequency of 50 Hertz. Let's first check the frequency. Frequency is 1 over period, which is 1 over. Period is 20 times 10 power negative 3. So this is 1 divided by 20 exponent negative 3. I think that is 50 Hertz. So the frequency is 50 Hertz. It is a sound wave, so it is longitudinal with a frequency of 50. So the answer is B. A cathode ray oscilloscope is used to display a wave of frequency 5 kHz. The display is shown here. What is the time-based setting? So frequency is 5 kHz. So and we know frequency is 1 over T, meaning the period is 1 over F, which is going to be 1 over 5,000, and the period is the length representing 1 cycle times the time-based setting. So 1 over 5,000 is equal to length representing 1 cycle is 2 boxes. Those are 2 centimeters. So that is 2 centimeters times the time-based setting x. So remember this one is in seconds. So I have 1 divided by 5,000, again divided by 2 centimeters. So you have 1 times 10 power negative 4 seconds per centimeter as the time-based setting. The answers are in milliseconds. We can check, there is milliseconds and microseconds. So let's check. If I change to micro, I will say divide by 1 exponent negative 6. That's 100. So the answer is going to be B. The answer will be 100 microseconds per centimeter. That is X. A siren emits sound of frequency 1000 Hz. The siren moves at 20 meters per second towards an observer who is standing still. The speed of sound in the air is 330 meters per second. Which expression would correctly give the frequency heard by the observer? Which expression would correctly give the frequency heard by the observer? So observe the frequency because it's moving towards, so we shall subtract. So this is V over V minus Vs times frequency of the source. So the observed frequency is going to be equal to V, which is 330, times frequency of the source, which is 1000, divided by 330 minus 20. So the answer is going to be B. A source of sound of constant power P is situated in an open space. The intensity I of sound at distance r from this source is given by that expression. I is equal to P over 4 pi r squared. How does the amplitude A of the vibrating air molecules vary with the distance r from the source? How does the amplitude vary with distance r from the source? Okay, so intensity is directly proportional to amplitude squared, which is equal to a constant times amplitude squared. How does the amplitude of vibration I of air molecules vary with distance r from the source? So intensity is inversely proportional to r squared, and intensity is directly proportional to amplitude squared. So let me just combine the two equations here. So combine this with I is equal to k a squared, assuming all these ones are constants apart from r. So it means a squared is equal to a constant divided by r squared. So the square goes off. The square goes off, which means amplitude is inversely proportional to r. The square goes off. So the answer is going to be A. Amplitude is inversely proportional to r because you get the square root both sides. In an experiment to demonstrate a stationary wave, two microwave transmitters emitting waves of wavelength 4 centimeters are set facing each other as shown here. A detector is moved along a straight line between the transmitters. It detects positions of maximum and minimum signal. The detector is a distance d from the left-hand transmitter. Assume that both transmitters are at antinodes of the stationary wave. Which row gives a value of d for a maximum and for a minimum? Which row gives a value of d for a maximum and for a minimum? Okay. So they said a detector is moved along a straight line between the transmitters. It detects positions of maximum and minimum signal. The detector is a distance d from the left-hand transmitter. Assume that both transmitters are at antinodes. So here there is an antinode and an antinode here. Which row gives a value of d for a maximum and for a minimum? If there is an antinode here, then let's see, the next antinode should be at a greater distance than the node. So let's see. The next antinode, which row gives a value of d for a maximum and for a minimum? So the next antinode should be at a greater distance than the node. So the answer can't be 40, it can't be A, it cannot be B, because A is showing the maximum is at a smaller distance than the minimum. And even this one is showing the maximum is at a smaller distance than the minimum, which yet will be the reverse. Then the reverse, we are seeing that the maximum here is at a greater distance than the minimum, but then assume that both transmitters are at antinodes of the stationary wave. Which row gives a value of d for a maximum and d for a minimum? So we are saying d for a maximum, if d for a maximum is 48 centimeters, then d for a minimum will be 47. If d for a maximum is 48, then D for a minimum is going to be 47. And then the question would be, why not 49 and 47? Why not 49 and 47? Okay, in an experiment to demonstrate a stationary wave, two microwave transmitters emitting waves of wavelength 4 centimeters are set facing each other as shown there. Okay, as shown there. A detector is moved along a straight line between the transmitters. It detects positions of maximum and minimum signal. The detector is a distance d from the left-hand transmitter. Assume that both transmitters are at antinodes. So there's an antinode here and another antinode the other side. Which row gives a value of d for a maximum? We have already seen that a maximum should be, if d is measured from an antinode, then the next antinode should be at a greater distance than the antinode. In other words, the antinode or the minimum should be at a smaller distance than the maximum, because we have started from a maximum. And therefore, that's why I said our choices would be between C and D. Now, why couldn't it be 49 and 47? Why couldn't it be 49 and 47? So this would mean the distance between two successive the distance between a maximum and A, here it would be 49, and the distance between A and a minimum would actually be 47. So this would not be very applicable. It would be a very great difference. So I will eliminate D. Okay. The graph shows how the height of the water surface at a point in a harbor varies with T as waves pass the point. What are P and Q? P is not amplitude. Amplitude should be here. Then Q can be wavelength. Q is wavelength. It is not. It is against T. So Q can be period. So we eliminate wavelength. But then P is not amplitude. So we can take displacement but not amplitude. It is not the maximum. The maximum displacement would be here. So it is not amplitude. It is displacement. Diagram shows a sketch of a wave pattern over a short period of time. Which description of this wave is correct? The wave is longitudinal, has a wavelength of 20 centimeters. Let's check the wavelength. This is one wavelength, two wavelengths and a half. So 2.5, which is 5/2 wavelengths, is equal to 100 centimeters. So wavelength is going to be 200 centimeters divided by 5. 200 divided by 5, which is 40. So the wavelength must be 40. So it means A and B are wrong. The wave is transverse and have a wavelength of 40. The wave is transverse, has a wavelength of 40 centimeters and is stationary. So it is transverse, having a wavelength of 40, and it is forming a stationary wave. It is not progressive. There is no transfer of energy there. The double slit experiment demonstrates interference between two coherent sources of light. Waves in the diagram, the curved lines represent wavefronts. At which point does complete destructive interference occurs? Remember, complete destructive interference occurs when a maximum meets with a minimum, or a trough and a crest interfere or overlap. So maximum, of course, these are showing if the lines represent wavefronts, let's say these are crests. These are crests. So in between the crests, those are going to be troughs. So this is B is wrong, that is constructive. Here we don't expect constructive. And D is a point in the center where we don't have we only have a crest, so that is wrong. So the answer is going to be C, because we are seeing C is there's a crest, there's this crest, then meeting with the trough of the other wave. So there is destructive interference at C. Light of wavelength 567 nanometers is incident normally on a diffraction grating. The grating has 400 lines per millimeter. A number of diffraction maxima are observed on the far side of the grating. What is the angle between the second order maximum and the third order maximum? So we know that theta, or n lambda, is equal to d sine theta, meaning theta is going to be equal to n lambda over d sine inverse. But then we know that d is equal to 1 over n, so n goes up. So theta is going to be the sine inverse of n times small n lambda. Yes, sine inverse of that. Okay, so let's check the first one. For the second order, theta 2 is going to be sine inverse of n. They gave us 400 lines per millimeter, which is 400 times 1000 to be lines per meter. So that will be 400,000 lines per meter. N is 2, and lambda is 567 times 10 power negative 9. 400,000 times 2 times 2 times 567 exponent negative 9, which gives us 0.4536. Then you get the sine inverse. Sine inverse of the answer 26. So theta 2 is equal to 26 or approximately 27 degrees. Okay, then theta 3, I'll call it theta 3. So theta 3 will be sine inverse of 400,000 times 3 times 567 times 10 power negative 9. So this is going to be 400,000 times 3 times 567 exponent negative 9. Shift sine inverse of the answer, which is 42. So theta 3 is equal to 42 point approximately 43 degrees. So we get a difference, theta 3 minus theta 2. 43 minus 27. 43 minus 27, that is approximately 16. So the answer is going to be C. That is 15.9, which is approximately 16. A cathode ray oscilloscope is connected to an alternating voltage. The following trace is produced on the screen. The oscilloscope time-based setting is 0.5. The Y plate sensitivity is 2 volts per centimeter. Which statement about the alternating voltage is correct? The amplitude is 3.5 centimeters. Let's check. 1, 2, 3 and a half. 3.5 centimeters times 2V per centimeter. So the amplitude is supposed to be 7, approximately 7 centimeters. 7 volts. So this is not the amplitude. The wavelength is 4 centimeters. Let's check the wavelength. We can't find the wavelength directly from here because we don't have the speed. This only gives us a frequency. So there is no way we can verify that the wavelength is 4 centimeters. Then the period is 1 millisecond. Let's check the period. Period is equal to 1 over it is L times X. Length representing one cycle is 1, 2, 3, 4, 4 centimeters. 4 centimeters times the time base setting, which is 0.5. Milliseconds per centimeter. So per centimeter is cancelled. And 4 times 0.5 is 2. So this is not the period, it's not 2, it's not 1 millisecond. So probably the answer is going to be B. We can also verify. So this is 2 milliseconds. This is 2 milliseconds. So the frequency is going to be 1 over 2 times 10 power negative 3. 1 divided by 2 exponent negative 3, which is 500. And 500 hertz is 0.5 kilohertz. So the answer is B. A wave has period T, wavelength lambda, and amplitude A. The wave is shown on the graph of displacement against distance, as shown here. Which graph is correctly labeled? So this is amplitude and this is wavelength. So this is correct. So the answer is going to be A. This is because it is x against distance. This is not period. This is not period because it's x against distance. And this is not, this is twice the amplitude, so this is wrong. The table lists possible orders of magnitude of the wavelengths of some of the principal radiations of electromagnetic spectrum. Which row shows the correct orders of magnitude of the wavelengths? Okay, so let's check microwaves. This is not this is radio waves, so this is D is wrong. 10 power negative 6. This is infrared. This is infrared, so this is going to be wrong. So we remain with 10 power negative 4 and 10 power negative 2. Okay, this could be microwaves because Rumenera's mother is visiting Uncle Xavier's garden. So this is on the left hand side we have 7 times 10 power negative 7. This is for red. So infrared must be around 10 power negative 6. So this is infrared, correct. This is not infrared, so this is wrong. So our answer is going to be C. A vehicle carries a microwave transmitter that transmits microwaves of a constant frequency of a constant frequency. A stationary observer has a microwave receiver. The vehicle moves directly towards the observer at a constant speed. The observer detects microwaves of frequency f0. The vehicle then accelerates, still moving towards the observer. That means the speed increases. The vehicle then accelerates, still moving towards the observer, travels at a higher steady speed for a time and then decelerates until it stops. What is the variation in the frequency of the microwaves that are detected by the observer? So let's say F naught is equal to V, because the vehicle moves directly towards the observer, so this will be V minus Vs times Fs. But then the vehicle then accelerates. That means the speed increases to a new value, which means because the speed increases to a new value, it therefore implies that the frequency here is going to raise. Because Vs becomes bigger, the difference becomes smaller, the frequency raises. So here they are saying the observed frequency will fall, so it will raise. The observer, still moving towards the observer, it travels at a higher steady speed, constant speed. So if the speed now remains constant, it means the observed frequency remains steady. So remains steady, then it decelerates. It means now the speed decreases, which means this difference becomes bigger, so the frequency here decreases. So raises, remains steady, and then returns to F naught, then remains steady, then falls to a lower frequency than F naught. It will not fall to a lower frequency than F naught because there is no way it shows it moves away from the observer. Therefore, it returns to the frequency F naught. So the answer is going to be D. Yes, let me see. The vehicle moves directly towards the observer at a constant speed. The observer detects microwaves of frequency F naught. The vehicle then accelerates, still moving towards the observer, then travels at a higher steady speed for a time, and then decelerates until it stops. When V becomes 0, F naught is going to be equal to Fs. When the speed becomes 0, because it comes to rest, meaning Vs becomes 0, it then decelerates. Then, so we are saying the observed frequency will raise, then remain steady, then return to the frequency F naught. The observed frequency will raise, then remain steady, and then fall to a lower frequency than F naught. Okay, so since this decreases to 0, then it is going to be lower because it started with a certain frequency when it was moving, where we had V is equal to V minus S minus Vs. So this is going to be a lower frequency than F naught. So the answer is going to be C. Okay. So the frequency, when it slows down, it is going to be lower than the observed frequency F naught. So the diagram shows a cathode ray oscilloscope display of an electromagnetic wave. So the speed is the speed of light. The time-based setting is 0.2 microseconds per centimeter. Which statement is correct? The frequency of the wave is 2.5 megahertz. Let's check the frequency. Because it is an electromagnetic wave with that time-based setting, this is 1 centimeter, so it means the period is going to be equal to 2 centimeters times 0.2 times 10 power negative 6 seconds per centimeter. So the frequency is going to be 1 over 0.4 times 10 power negative 6. 1 divided by 0.4 exponent negative 6. So that is 2.5, 3, 2.5 megahertz. So the frequency is 2.5 megahertz. We ignore this one and this one. Okay. Then the region. And it lies in the microwave region and it lies in the radio wave region. Let's check this. So wavelength is equal to V over F. It is electromagnetic, 3 times 10 power 8 over F, which is 2.5 times 10 power 6. So we have 3 exponent 8 divided by the answer. That is 120. That is automatically radio wave. So the answer is going to be B, because the wavelength is equal to 120 meters. That is B, the longest wavelength. In a double slit experiment, interference experiment, light of frequency 6 Hz is incident on a pair of slits. Bright fringes that are 3 millimeters apart are observed on a screen some distance away. What is the separation of the bright fringes when the frequency of the light is changed to this? So since it is a double slit, you must be noting that lambda is equal to AX divided by D. So what is the separation of the bright fringe when the frequency of the light is changed to that? So let's check. For double slit, remember wavelength is inversely proportional to frequency. And this is light, so we know the speed of light. So we shall simply say lambda is equal to V over F. So let's check. I'll come up with two equations. For the first one, light of frequency that, so V is 3 times 10 power 8, frequency is 6 times 10 power 14 is equal to A. Bright fringes that are 3 millimeters apart are observed on the screen some distance away. So it's equal to A, which is the slit separation, times 3 millimeters. I will not change 3, divided by the distance D. So we repeat the same for the other one. The speed is still 3 times 10 power 8. The wavelength, the frequency is changed to 5 times 10 power 14. This is equal to A times X over D. So we just combine these two, because we want to find what is the separation of the bright fringes. We want X. So we just divide the two equations. When I divide the two equations, I have that X over 3 is equal to, dividing the two equations, this divide by that one, 3 times 10 power 8 goes off, so I remain with 6 times 10 power 14 divided by 5 times 10 power 14. So 3 times 10 power 8 cancels out, just like here A over D cancelled out. So it means X is going to be 6 exponent 14 divided by 5 exponent 14 times 3, which is giving me a value of 3.6. So the answer is going to be 3.6 millimeters. So X is 3.6. A tube of length L is open at both ends. A stationary wave is set up in this tube when a tuning fork vibrating with the frequency Fx is held at one end. This is the lowest frequency of the stationary wave. If it is the lowest, that is very simple. So we have for the lowest, Fx is equal to V over, this is a quarter plus a quarter, this is L is equal to a half wavelength. So this is V over wavelength, which is going to be equal to V over 2L. Another tube of length 2L is closed at one end. A stationary wave is set up in this tube. When a tuning fork vibrating with frequency Fy is held at the open end, this is the lowest frequency of a stationary wave that can be formed in this tube. So for the closed one, the lowest is going to be this one here. This is a quarter cycle. So 2L is equal to a quarter of wavelength. So this means Fy is equal to V over wavelength, which is equal to wavelength is going to be 4 times 2L, which is 8L. So this is going to be V over 8L. Assume the end correction for each tube is negligible. What equation is correct? So let's combine these two. Fx is equal to V over 2L and Fy is equal to V over 8L. You notice that when I multiply this one by 4, I get that one there. So in other words, Fy times 4 is equal to Fx. When I multiply V over 8L by 4, I get Fx. So Fx must be equal to 4 times Fy. So the answer is going to be D. When I multiply by 4, it takes me to that. Which statement gives a condition that enables diffraction to occur? So we have a source of waves moves towards a stationary observer. A wave is partially blocked by an obstacle. So this one causes diffraction. Two coherent waves are superposed, that does not cause diffraction. A transverse progressive wave is set up on a string. The graph shows the variation with the time of displacement for a point on this string. Okay. The separation xy on the graph represents the dash and the dash. The dash 1 dash of the wave. X and y have equal dash 2 dash. So which word completes gaps 1 and 2? So X here, it is vibrating vertically upwards, Y is vibrating vertically upwards. Okay, so they are the same position there. So this one is going to be wavelength. Distance between two corresponding points that are in phase, that is wavelength. X and Y have equal, so this distance is the same from equilibrium, so they have equal displacements. So the answer is wavelength and displacements, which makes the answer to be, this is not wavelength because this is displacement against time, so that is period. The separation xy on the graph represents period. Period because this is against time, so the answer there is going to be a time period and displacement. Which region of the electromagnetic spectrum includes waves with a frequency of 10 power 7 megahertz? Let's check the wavelength. So wavelength is going to be V, which is 3 times 10 power 8 divided by frequency, which is 10 power 7 times 10 power 6. So this is going to be 3 exponent 8 divided by, I'll simply say 1 exponent 7 and 6, that is 13. So which is 3 times 10 power negative 5. This is on the left hand side of the visible spectrum, which is most likely infrared. So the answer here is going to be infrared. Because when you look at the visible spectrum, Rumenera's mother is visiting Uncle Xavier's garden. This is 7 times 10 power negative 7 on the left hand side, which is red. The other one is 4 times 10 power negative 7 on the left hand side, which is violet. So power -5 must be on the left hand side next to visible, which is going to be infrared, because radio waves would be far, ultraviolet is on the other side, X-ray is on the other side. What can be deduced from a table of wavelengths of the waves in the electromagnetic spectrum? Green light has a shorter wavelength than X-rays. We can check. Green light is in the visible spectrum. It has a longer wavelength than X-rays, so that is not true. Red light has a shorter wavelength than green light. Red has a longer wavelength, so this is not true. The wavelength range for radio waves is less than that for infrared. Radio waves have the highest wavelength, so that is not true. The wavelength range of X-rays is less than that for radio waves. That is very true. Radio waves have the highest wavelength. X-rays have a smaller wavelength. A binary star consists of two stars rotating about around a common center. Light from one of the stars is observed on the Earth. The observed frequency of the light varies between a minimum frequency F minimum and a maximum F max. The rate of rotation of the binary star increases. What is the change of F max and the change to F minimum? So F maximum is going to be obtained here when it is just moving towards, and F minimum will be here when it is just moving away. And they are saying the rate of rotation of the binary star increases. So if it is towards, F is equal to V over V minus Vs times Fs. So if the rate of rotation of the binary star increases, it means the speed Vs increases. And if the speed Vs increases, it means this difference here becomes even smaller, so the frequency here increases. So the first part, it increases, F max increases, then F minimum, this is F max. F max, F minimum is equal to V over V plus Vs times Fs. So if the rate is increased, it means this is bigger, which makes this one smaller. The denominator becomes bigger when Vs increases, which makes F minimum smaller. So this one decreases. So the answer is going to be C. The diagram shows two sources of waves, S1 and S2. The sources oscillate with a phase difference of 180 degrees. That means where we expect a minima, we must find there a maxima, and the reverse is going to be true. The sources each generate a wave of wavelength 2 centimeters. Each source produces a wave that has amplitude x0 when it reaches point P. What is the amplitude of the oscillation at P? So first of all, let's find the path difference, ignoring the phase difference between the sources. The path difference is going to be equal to 113 minus 5, which is going to be 8 centimeters. If the phase difference was to be 0 between the sources, then we would get path difference over wavelength would be equal to 8 over the wavelength is 2. Wavelength is 2. This will give us 4. In other words, the path difference would be 4 times lambda. This would be constructive interference. But because the phase difference between the two sources was actually 180 degrees, where we would have a maximum would therefore be a minimum. So since the sources are 180 degrees out of phase, then instead of having a maximum at point P, we are going to have a minimum, which corresponds to destructive interference, and therefore the amplitude at P is going to be 0. Amplitude at P is going to be 0 since the phase difference between the sources is 180. However, if the phase difference between the sources was 0 degrees Celsius, then here at P, we would have a maximum which would give us twice x naught. I hope that is very clear. Remember, when the phase difference between the two sources is changed to 180 degrees, where there was a maximum, there will therefore be a minimum. The maxima and the minima swap places or swap positions. Two lasers emit light in a vacuum. One laser emits red light and the other emits green light. Which property of the two laser beams must be different? So the speed is the same, so this is no different. The intensity, two lasers emit light in a vacuum. One laser emits red light. So red light and green light, they are varying in the frequency. Because the wavelength is different here, the frequency is going to be different. So the answer there is going to be B. The frequency must be different. The diagram shows the screen of a CRO displaying a wave. The time base of the CRO is set to 10 milliseconds per division. What's the frequency of the wave? So the time base 1, 2, 3, 4, 5, 6. I'm looking for one cycle. 7, 8, 9, 10. It is hard to use 10. Let me check again. I want very clear points where I can tell the distance representing one cycle. So I have, let me look very keenly. Okay, let me just take an estimate. Of course, we shall see what rounds off these ones. Let me just take an estimate up to around here, which is a very hard estimate. So let's say this is 1, 2, 3, 4, and remember, I'll divide this into half a division. Let's say 4 and a quarter a division. 4 and a quarter a division, representing one cycle. 4 and a quarter division representing one cycle. Yes, let's use 4 and a quarter division representing one cycle. This is going to be 9 over 5, 9 over 4 divisions. That is, no, not 9, 16. Not 16, where is my mathematics? So one cycle is represented by 4 and a quarter divisions, which is 4 times 4, which is 16, 17 over 4 divisions. We shall just round off one of these values. So let's find the period is going to be 17 over 4 times 10 times 10 power negative 3. Then the frequency is going to be 1 over 17 times 10 times 10 power negative 3 divided by 4. So let's see, this is going to be 1 divided by open brackets 17 times 10 exponent negative 3. Divide this by 4. So this is, did I compute this correctly? Period is 17 over 4 which makes this 4 divided by open brackets 17 exponent 17 times 10 exponent negative 3, which is 23.5, which is approximately 24. Therefore, the answer here is going to be D. A string is fixed at one end and the other end is attached to a vibrator. The frequency of the vibrator is slowly increased from 0. A series of stationary waves is formed. Assume that, that for a stationary wave there is a node at P. There is a node there. Of course, there must be another node at the fixed end. What are the first 5 wavelengths of the stationary waves that could be formed? This is a string. So for a string, we know that for the fundamental mode, we would have something like this for the fundamental. So that means L for the fundamental would represent half a wavelength, which would be 2L. Which would imply that 2L is equal to wavelength. So the first must be 2L. So the first must be 2L. The first must be 2L. So this is 2L over 2, 2L over 3. So the answer is just 2L over 1. The first wavelength is 2L over 1. We can check the second one. The second one, we shall have something like this, which is L. So that means the second one, L is equal to lambda, which is this one here. 2L over 2 is still L. The third one, we just go on increasing. So the answer is going to be A. Which region of the electromagnetic spectrum has waves of wavelength 1,000 times smaller than the wavelength of visible light? Wavelength of visible light is approximately 10 times 10 power, 10 power negative 7, then times 1,000, which becomes 10 power negative 4. X-rays is wrong because Rumenera's mother is visiting Uncle Xavier's garden. Visible is 10 power negative 7. When I get negative 4 is this side, so it must be microwaves or infrared, one of the two, micro or infrared. But most probably, which region of the electromagnetic spectrum has waves of wavelength 1,000 times smaller? 1,000 times smaller. So that means it is times 10 power negative 3. It is 1 over 1,000. So times 10 power negative 3 or 1. This is divided by 1,000. So this would be 10 power negative 10. That is 10 power negative 10. I think 10 power negative 10 is automatically X-rays. Not that one, don't even think much. 1,000 times smaller. We divide by 1,000. That is 10 power negative 10 meters, which will be X-rays. The diagram shows apparatus for the measurement of the frequency of a sound wave. The sound of the unknown frequency is reflected back from a metal plate. A microphone placed at a distance d from the metal plate detects the sound intensity. A minimum intensity is detected with the d equals to 12 centimeters. The plate is moved further away from the microphone until the next minimum is at d equals 15. So distance between two successive points of interference is equal to half wavelength. So this is going to be half. So it means distance, which is 15 minus 12 is equal to half wavelength. So the wavelength is 15 minus 12, that is 3 times 2, which is 6 centimeters. Wavelength is 6 centimeters. What is the frequency? It is sound. They gave us the speed of sound, so we can find the frequency. Frequency is going to be V, which is 336, divided by wavelength, which is 6 times 10 power negative 2. So 336 divided by 6 exponent negative 2. That gives us 5,600, which is C. 5,600, which is C. Okay. An astronomer observes a light, the light from a star that is moving away from the Earth. For the observed light, what has been increased due to the star's motion? It is moving away, so that is wavelength. Wavelength has been increased, the frequency has been reduced. The diagram shows a stationary wave at time t equals to 0 that has been set up on a string between points P and S. The nodes of the stationary wave occur on the string at P, Q, R, and S. So there's a node here, there's a node here, there's a node here, there is a node there. Point X is moving down at t equals to 0. The points on the string vibrate with time period t and maximum amplitude 2 centimeters. The displacement S is positive in the upward direction. Which graph best shows the variation with time with the t of the displacement S of point Y on the string? Point Y on the string. So they said X is moving down at t equals to 0. And if I put here a node and another node there and another node there, this, if X is moving downwards, a point here would be moving upwards, a point here is going to be moving downwards. So they must be moving in the same direction for Y. So this one is showing it was moving, it would be moving upwards. These two are wrong, so we have this and this. So this one is showing, they said the points on the string vibrate with t, with time period t. Time period is t and maximum amplitude 2 centimeters. So these graphs are showing half a period. It means at half a period, it means they have not reached maximum displacement of 2 centimeters. Because the maximum amplitude is 2 centimeters, and here we are having half period. It means for half period, the maximum displacement must also be half of 2 centimeters. So the answer is going to be A, because this is showing almost 1 centimeter. Okay, lastly, for this video, a two-source interference experiment uses the apparatus shown. What is the main purpose of the single slit? So the single slit is going to produce a single source of light, or a coherent source of light, because we need coherency for light to undergo interference. So the answer is going to be C, to provide coherent light. Okay, let's stop part 3 at this point. We shall start from this point in part 4. Okay, so bye bye.